All right, gang. In the last video, we ended up with this and the motivation. Let me see if I can get that a little bit clearer. Yeah, it's better. What happens when the standard deviation is not known? Now, I want to spend just a little bit more time with this, working with sigma being known. And what we talked about is we had these certain levels. Let's just call it. And we saw that when we had 95%, this Z critical turned out to be plus or minus 1.96. Now, other levels of confidence that we use are 99% and 90%. By far, these are the three most commonly reported levels of confidence, and that's why I want to tap into the central limit theorem and see what two Z critical Z values separate out the middle 90% and 99%, as we did with the 95%. So, guys, very quickly, let's just come down here and do the 90 first. So we know between two values, we have 90%. So how much are we missing? We're missing 10%. Put half here, half here. And we should be able to quickly do that with our calculator, just like we did before. So go inverse norm. So I want to concentrate on this one. I have 5% below. So negative 1.645. Now I'm going to go out to three places here because that's kind of a tricky rounding. It's not really tricky. It's just so close to 5,000 right there. So I'm going to go negative 1.645. And again, by symmetry, because we know the mean, the standard normal distribution is 0, that this is going to be 1.645. So plus or minus 1.645. Now the 99% is going to be the same kind of exercise. Between two values, we have 99% of the distribution. So how much are we missing? 1%. So we need 0.5% and 0.5%. Same thing, guys. Inverse norm. 0.5% as the decimal is 0.005, 0.1. So we get negative 2.576. So we should know by now that it's going to be plus or minus 2.576. Guys, this whole thing here works on the standard deviation being known. Well, what happens when the standard deviation is not known? Well, we can't use this distribution because this was built on that assumption. So guys, and again, this over here is called a Z distribution. You might say, Darbo, you're going through this kind of fast. Guys, I've taught you this before. We've talked about this back in normal distributions. We've talked about it in the central limit theorem. It's time to just touch on this, but move on to the new material. Remember, the Z distribution normal distribution has a mean 0, standard deviation 1. When we're talking about the distribution of sample means, if the conditions are satisfied. But guys, I want to talk about this sigma not known. And what we do in this situation is we have a completely new distribution that models our problem called the T distribution. Now, the Z distribution has a mean of 0, standard deviation of 1 always. The T distribution has a mean of 0, but the standard deviation varies according to the sample size. So guys, the T distribution is completely and totally defined by what we call the degrees of freedom. And we're very creative in statistics for the abbreviation for degrees of freedom. It's just called DF. And it's very easy to find. It's just a sample size minus 1. So if I wanted to find this, not for a z distribution, but I wanted to find the two values between which 90% of the distribution is found, and the population standard deviation is not known, I got to use the t-distribution, but I have to know the sample size. So just as an illustration here, let's say that the sample size is 40. Then I know my degrees of freedom is 40 minus 1. So to find the value, no longer the z-critical, but the t-critical in this problem, because we're drawing from a t-distribution, and I want to find the middle 90%. There's a couple of these on your assignments, so that's the reason I'm going through this kind of diligently, patiently, I hope. Same thing, okay? Same thing before. What we got? We got 90% between here and here. How much we missing? 10%. Half goes here, half goes there. That doesn't change. But what does change is when we go to our calculator, we don't go to inverse norm unless you want to get the problem wrong. You go to inverse t. Now some of you, if you got older calculators, you're going to go to inverse t, and you're not going to be able to get your value, but you're not going to see inverse t on your calculator. I'm going to show you guys what to do on R to get the same values. So inverse t, all right. Now I want 0.05 goes below. But now instead of putting 0, 1, what I put degrees of freedom. You don't put the mean, you don't put the standard deviation, you put degrees of freedom, because this new distribution, this t distribution, is totally defined by the degrees of freedom. Now, negative 1.685 means 0. Because of symmetry, we know this has to be 685. So, does the t-distribution for 90% always result in negative 1.685 and positive 1.685? No. It depends on the degrees of freedom. Depends on the sample size. If I have n equal 50, then this is going to change. And let's just see what happens. I mean, n equal 50 would do what? Well, I'd have a different degrees of freedom. And notice I'm going to get a different t-critical. Even though I'm still calculating the 90%, I'm going to get a different t-critical. It's off by, you can see how much it's off. Now, what if you don't have a calculator that has the t, the inverse t? Well, it's kind of cool because R has something that does work. All right, let me get out of here and get R up here. And it's just called PT. No, it's called yeah, PT. So if I go 0.05 comma 39, no, that's the percentage, guys. I'm losing my mind here. It's QT. First mistake I've ever made. All right, if you do QT, you get the right thing. Don't do PT. All right, let's make sure. Don't do PT. That was a Darbro bozo moment. All right, use QT. So again, if I wanted to, you can see that it gives us exactly what we had before. And if we, same illustration, we had a sample size of 50, our degrees of freedom would be 49. So we get negative 1.676551, just like we did on the calculator. All right, so if you don't have the calculator, just pop up R. It's easy, it's free. And it calculates the same thing as does your calculator. All right, gang. Let's get to some good stuff. So what do we know? Back before, when sigma was known, we saw that we could estimate mu by taking x bar minus, and this, let's just focus on the 95% confidence interval, z critical, sigma over the square root of n. Now, 95% was 1.96. Remember seeing that from the previous video? All right. But what happens now when we move into more realistic, not known? Well, we still use a sample mean. We still have the plus or minus for reasons we talked about earlier, but we can't use a z-critical because it was built on this assumption. What distribution happens when the standard deviation of the population is not known? The t-distribution. Sigma is not known. What would be the obvious replacement? The sample standard deviation over the square root of n. Now, guys, this is very important here. Let's give each one of these things a name. This is called our point estimate. I know that looks like paint estimate, but it's not supposed to be. It's supposed to be point estimate. This is called our t-critical. This is still called our standard error. And all of this right here is called our margin of error. So that's going to play a critical role in what we're doing. All right, there's been a new test that's come out. Let's say that there's a new achievement test. We don't know anything about the mean or the standard deviation. So all this is unknown. So we give this new test to 5 students at Shawnee State. One scores 111. The other scores 114. The other scores 129. The other scores 82. And the other scores 94. Now, this is a sample of 5 students, and we want to take the sample mean and use it to estimate the mean score for all students at Shawnee State. So what we're going to do here is we're going to construct a confidence interval. Now, to construct a confidence interval, at least for now, is 4 things that you need. You need the sample mean. You need the sample standard deviation. You need the sample size. And you need t-critical, right? 1, 2, 3, 4. Well, can we get that? Well, absolutely we can get it. Let's put this information in our calculator. All right, we'll clear this out. So go clear, enter. So 111, 114, 129, 82, and 94. So go to stat, go over to one variable stats, go to L1, and the mean is 106. Standard deviation is 18.293 or 18.2893. You guys don't use that one. That's the population standard deviation. Guys, you'll never use this. I wish they didn't put that on the calculator because that really doesn't help you much. That assumes if these 5 scores were your population, that would be the calculation of the standard deviation. Guys, we will always use SX. So 18.2893. Sample size, well, this one we can count, but just, if it's a larger data set, it'd be harder to count, so we have 5. Then we need T star. Let's do it. And again, let's just focus on calculating the 95%. So, guys, same old song and dance, right? Between two values falls 95% of the distribution. How much is missing? 5%. Half goes here. Half goes here. Put it in our calculator. So what's half of 5%? 2.5% is the decimal 0.025. This thing is defined by our degrees of freedom, which is n minus 1. So we have negative 2.7764. Right? All right. Gang, it's time for plug and chug. X bar, plus or minus, T critical, standard deviation, over the square root of n. X bar is 106. T critical is 2.7764. The standard deviation is 18.2893. Our sample size is 5. I've seen students before, they apparently are so impressed with this degrees of freedom that they think they're supposed to put a 4 there. It doesn't say the square root of df. This is the square root of n. And n is your total sample size. So if we can put this in our calculator, then we will get the bounds for our confidence intervals. So I'm going to do the left side first, and I would encourage you to always do that. So 106 minus 2.7764 times 18.2893 divided by the square root of 5. All right. Now I want to do the same thing, so I'm going to do my entry. And the only thing I need to do is come over and change my plus sign. So my left bound is 83.29. And my right bound is 128.71. So guys, that says if we took many samples, 95% of the time, the mean, so there's a 0.95 probability that this interval will capture the unknown mean. All right, so keep that handy. All right. So let me show you another way. So ways to calculate confidence intervals for means. Number 1, by hand. Done. Number 2, your TI-84 calculator. Number 3, R. You're going to find out that these are so much simpler than that. Okay? So if I want to do my TI-84, I'm going to go to Stat, I'm going to go over to Test, and I'm going to come down to what's called a T interval. Now, why do I think T? Well, it's modeled by the T distribution, like I just have been talking about. I have my data in L1 already typed in. Now, if I have the statistical results, let's say I have the mean and the standard deviation and stuff I want to type in by hand, I could do that, and it's already imported that in anyway. But in my case, since I've typed the data in L1, I'm just going to let the calculator go to L1 and do all the calculations. So I want 0.95 and do calculate, and you will see that we get the same thing, 83.291. I rounded to 2 places. It went 3, that's fine. And 128.71, which is the same thing here. Wham, bam, thank you, man. You got your T interval in about 3 seconds. Up here it takes longer. But I just want you to know there's a formula behind the scenes that's driving this calculation here. Now, what if the cat, dog, alligator, whatever pet you may have, ate your calculator? Say, Dr. Darborough, I can't get my assignment done because my alligator ate my calculator. Well, no. What I would do here is I would just create my data. Then we'll type these numbers in. So I have 111, 114, 129. Has anybody got a pet alligator? That'd be kind of scary. If I was in class, I would tell you my alligator story. I have a thing for messing with alligators. Maybe I have a death wish. I don't know. All right, so I got my data in. So these are the data. In my calculator, those are called L1. Here it's going to be called data. All right. So what I do here is I use something called a t-test, but there's a little caveat to it that we can use. So let me get my bearings here. So if I want to do a t-interval, I actually kind of strangely do t-test. And this is going to make sense because the next thing on the agenda is a t-test. So I have t-test and I want to do this on my data, but I want to do my confidence level at 0.95. And then all I want is my confidence interval. And when we do that, you'll see that we get 83.29, which is exactly what we got before, and 128.71, which is exactly what we got before. All you got to do, guys, is just be careful when you type in type this into R. Okay, so by hand, by the calculator, or by R. I'm okay with either. Now, one more thing. Really, I don't think that we need to do a lot of illustrations here. I'll do one more, and then I want to talk about some other stuff. But really, we haven't got much longer on this video, or we shouldn't have, unless I go crazy. So let's say we this is kind of example number 2. Let's say we collect a random sample, and we get an X bar of 42.8, a standard deviation of 11.5, and sample size is 50, and we want to construct a confidence interval at 90% for our unknown mu. So guys, how are you going to do this? Well, you got 3 choices. By hand, using the formula, your calculator, R. Now R is a little tougher because the illustration I gave you, you would need the 50 measurements to type into R to be able to get the confidence intervals. So really, when you're given the summary statistics, you really just got one of 2 choices. Well, gang, I'm going to use the calculator. It works. It's simple. And it gets the right answer. All right, so T interval. Situation, I've got the statistical results, not the data. So my mean is 42.8. My standard deviation is 11.5. My sample size is 50. And my confidence interval, I want a 90% instead of a 95. You can use 0.90 or 90, whatever turns you on there, go for it. Yeah, there you go. 40.07. And 45.53. So there's a 0.95 probability this interval contains the unknown population mean that we're trying to estimate. Guys, it's that simple. Now, one additional item. How does the width of the interval or the margin of error, change when we have a change in the following conditions. First of all, what would happen if we increase the confidence level? And just for a talking point, if we went from 90% to a 95% back here, how would this interval change? Well, pretty simple, right? If we have the T critical between 90% and we want to widen it to 95%, what's going to happen to the T critical? This one's going to be bigger, isn't it? So when I go back to my formula and multiply by a bigger number, what's going to happen to the width of my interval? It's going to get bigger. The margin of error, the width over here, is going to get bigger. So if we increase the confidence level, the interval will get larger. Grab a sheet of paper here. I thought I was going to be able to put it on one sheet of paper, but I couldn't. All right. Second thing, lower the standard deviation. How does that impact? Well, gang, just like we did before. Let's go back to our confidence interval formula. If I make this value smaller, let's set the confidence level. Let's just go back to 90%. Let's set it. That's not going to move. But let's just focus on changing this. If I lower this value, what happens? I multiply this by a lower number. I'm going to get a smaller number divided by the same sample size. I'm going to get a margin of error that's smaller. So a lower standard deviation decreases the margin of error. Now, what about increasing the sample size? What's that going to do to our intervals? Is it going to make it wider or narrower? Again, let's just focus on this right side like we've been doing before. Keep that constant. Don't change that. Standard deviation, keep it constant. Don't change it. What happens when we make this bigger? Well, when you increase the denominator in a fraction, the fraction gets smaller. So if you multiply your T critical by a smaller value, which is the result of increasing the sample size n, then you're going to get a smaller margin of error. So a smaller width smaller margin of error. All right, so gang, let's go back and think this the other way. What happens if we decrease the confidence level? We went from 90% to 80%. What would happen? Well, we would decrease our confidence, our margin of error. When we increased the confidence level, we increased the margin of error. By the same logic, if we decreased, we would get a smaller T critical, and we would decrease the margin of error. What if we got a higher standard deviation? Well, then we're going to increase. By the same logic before, if we put a bigger number there, we're multiplying our T critical times a bigger number, we're going to get a bigger margin of error on the right-hand side. What if we decrease the sample size? Well, if we decrease the sample size, go from 30 to 5, we're going to what? Decrease this value in a fraction. If you decrease the denominator, the total value of the fraction gets bigger. Bigger times that gives you a bigger margin of error and more width on your confidence interval. Guys, I am done. Don't let this stuff get you down. This should be some of the easier stuff that you do. Let me just make sure I made a few notes of things that I wanted to accomplish. Let me make sure that I accomplished what I wanted to accomplish. Um, I mean, I can't think of anything that I forgot. Yeah, and I'm not going to calculate a lot of these because I don't think you need that many examples. Um, oh, one more thing. Just kind of for clarity on your assignment. Uh, some of your assignments will talk about looking at a t-distribution table. I don't teach tables. I think tables are well, I think it's kind of like taking a horse and buggy. If you want to go to Columbus this weekend, take a horse and a buggy, or you're going to jump in your car. I think tables are outdated. With the technology that we have with R, as easy as technology is to get for these problems. So I don't teach tables. So if you see the reference to tables on my math lab, just think, well, Darbo doesn't teach that. He teaches this by the calculator, so use your calculator. So, what'll happen? Somebody decides, well, I don't need to watch the videos. I'll just do the assignments, and they'll get to the table thing and start using it. And so, if you do, sorry. All right, gang, have a good one.